So what we are studying is the subject of normal subgroups and quotient groups. And so let's just recall the basic definition. A subgroup H of a group G is normal if it satisfies any one of the following equivalent conditions. So any one of these implies all the others. So the first is that the left coset SAXH equals the right coset HX for every element of the group. Second equivalent condition is that the left coset is contained in the right coset for all X in the group. Another condition is that if I conjugate the subgroup H by X, that is, I look at the set XH, X inverse, that's always the same as H for all X in the group. The fourth is that the conjugate of H by X is always contained in H for all X in G. And the fifth, which is very important, is if I take the left coset XH and the right coset YH, and I take the product of these two sets. So this is everything I can write in the form an element in XH, XH1, times an element in this left coset YH, so YH2. So for all H1, H2 in H, this is the same as the left coset XYH. So I have a way to intelligently multiply left cosets. And these are equivalent conditions. And if you want to know how common or uncommon are normal subgroups compared to ordinary subgroups, the first statement is that in an abelian group, every subgroup is normal. Because the left coset XH, this is everything you can write in the form X times H, where H runs through all the elements of the subgroup H. But XH is equal to HX because the group is abelian. Multiplication is commutative. So in an abelian group, every subgroup is normal, and you don't have to worry about it. In a group which is not necessarily abelian, the subgroups consisting just of the identity and the subgroup, which is the whole group, are always normal subgroups. Because, for example, if you let X just be the set containing only the identity, XH, the left coset, is X times E. That is, it's X times every element of H, and the only element in H is the identity, which is just X, which is, of course, the identity times X, because E is the identity, which is H times X. So for every element in G, the left coset equals the right coset. And if you let H be equal to the whole group, XG, which is everything of the form X times, let's say G for G and G, well, in the group, every element is of this form. This is just the group, right? Because for y in the group, y is equal to x times the element x inverse y. So that's in xg. So every element is in this left coset. And similarly, every element is in the right coset. So the two sort of trivial subgroups of a group that are normal are the identity and the whole group itself. And we actually say that what is called a simple group, they're not necessarily simple, but a simple group is a group whose only normal subgroups are the identity and the group itself. So for example, if P is a prime number, the group G of congruence classes mod P is a simple group because, well, this is abelian, so every subgroup is simple, but this has no subgroups other than 0 in the whole group, because the only subgroups of G are 0 and the whole group. And the proof of this is a nice example of a fact we proved already. So recall the fundamental theorem about congruences, linear congruences. AX congruent to B mod M. So you fix A, B, and M. Can you solve this congruence? Can you find an X? If and only if B is congruent to 0 modulo the greatest common divisor of A and M. So suppose we let M equal to P a prime and A not congruent to 0 mod P. So P doesn't divide M. So the greatest common divisor of A and P has to be 1. Right? What's the greatest common divisor of A and P? It's a divisor of the prime P. So it's either 1 or P. And if it's not P, it has to be 1, which means that AX congruent to B mod P has a solution for all B. So let's go back to the example. Suppose we let G be the congruence classes mod P and let H be a subgroup of G and not just the identity 0. So that A, this means the congruence class, that A be in Z mod PZ, A different from 0. And A in H. So H is a subgroup. So then AX is in H for all integers X, right? If A is in the subgroup, A plus A, which is 2A is in the subgroup, 2A plus A is 3A and so forth, right? For all B in Z mod PZ, by what we just proved or recalled, there exists in X an integer or X and Z mod PZ, such that AX is congruent to B mod P, which means B, which is in AX, is in H, which means H is the whole group. So if P is a prime, and you look at the congruence classes modulo the prime P, the only subgroups are 0 and the identity. Right? So that's a basic fact in arithmetic, and it's a basic fact in group theory. All right. Are there questions about this? Do I need to explain more? Okay. By the way, so kind of related to that, if the integer m is composite, that means not a prime, then Z mod MZ is not a simple group. And the proof of that is the following, simple enough. M is composite, so we can factor it. So let's say M is D times K, where D is an integer strictly between 1 and M. It's a proper divisor of M not equal to 1. So let H be the cyclic subgroup generated by D. So this is the cyclic subgroup generated by D. So this is all multiples of D. I'll just write, I forget the plus MZ, 0, D, 2D, 3D. You get up to K minus 1 times D. And KD, these are all congruence classes, K times D plus MZ is M plus MZ, which is 0 plus MZ. So I have here K elements in this cyclic subgroup, and K is also between 1 and M, because dk is equal to M. So this is a subgroup. It's not equal to 0, and it's also not equal to the whole group. So the additive group of congruence classes, mod M, is simple if and only if M is a prime number. And the integers mod M is an example of an additive abelian group that's cyclic. If we write this in multiplicative language, suppose we let G be the cyclic group of order M generated by X. So this means G is all powers of X. E, X, X squared, X cubed, and so forth. And X inverse squared, X inverse cubed, and so forth. But because this is a cyclic group of order M, that means X to the M is the identity. So when you're taking the positive powers of X, you get up to X to the M minus 1. If you multiply this again by X, you get the identity. You're back where you started. And if X to the M equals the identity, that's equal to x times x to the m minus 1, it means that the inverse of x is x to the power m minus 1. So each of these negative powers is a positive power, and the positive powers stop at m minus 1. So these are the elements of the cyclic group of order m. And if m is prime, then G is simple, is a simple group, has no proper subgroups. If M is composite, then G is not simple. So for example, if we take a group of order 6, cyclic group of order 6, it consists of these 6 elements. So this is the cyclic group of order 6. Suppose that H be the subgroup generated by x squared. So that's the identity, and you just take powers of x squared. X squared squared is x to the 4th. X squared cubed is x to the 6th, which is the identity. So this is a subgroup of G, and it's not equal to G, and it's not equal to just the identity. I can also take the subgroup generated by x cubed. So it's the powers of x cubed. E x cubed. What's the next power of x cubed? If I square this, I get x to the 6th, which is the identity. So this is just another subgroup. This contains 2 elements. Suppose I take the subgroup generated by x to the 4th. This is E, x to the 4th. If I square it, I get x to the 8th. But 8 is 2 plus 6, so this is x squared times x to the 6th. X to the 6th is the identity, so this is just x squared. If I square, if I multiply this by x, I get x to the 6th, I'm back to the identity. So the subgroup generated by x to the 4th consists again of these same 3 elements. It's the same as the subgroup generated by x squared. And if you check, the subgroup generated by x to the 5th is going to be the whole group. Right? So this is actually a very nice example of a cyclic group, and it's worth spending some time making sure you understand every one of these statements. Okay. Any questions about this? So in the notes, what is theorem 7, which deserves a star, says the following. If H is a normal subgroup of a group G, then the set of cosets G mod H, this means the set of all left cosets XH for X and G. But if it's normal, of course, every left coset is equal to the right coset. So we can use left and right cosets interchangeably. So this set of cosets is a group with the binary operation xh times yh equals xyh. The product of these two cosets is this coset. And the identity element is just the coset h. This is the left coset E times h. And because for a normal subgroup, this operation is well defined, it's straightforward to check, as I did on Wednesday last week, that this is a group. Let's look at some examples. So suppose I take G to be the cyclic group of order 6. Suppose I let H be the subgroup generated by x squared. So it's the subgroup that consists of these three elements, E, x squared, and x cubed. So Lagrange's theorem says that the index of G and H, which is the order of G divided by the order of H, a cyclic group of order 6 contains 6 elements. This subgroup contains 3 elements. 6 over 3 is 2. So the order of the quotient group, G mod H, is 2. It's going to have 2 elements. One of them is H. What is XH? This means take everything in H and multiply it on the left by X. That's X times E, X times X squared. Oops, sorry, this should be X to the 4th. X times X to the 4th. That's equal to X, X cubed, and X to the 5th. So this is a left coset, and it's not equal to H, which is E, X squared, and X to the 4th. So these are the 2 left cosets in the quotient group. G mod H consists of H and XH. And if you look at the group G, H has the elements E, X squared, and X to the 4th, and XH has the elements X, X cubed, and X to the 5th. So this is the group G with its 6 elements, and G mod H partitions G into these 2 cosets. This is H. Those 3 elements. And this is XH. These 3 other elements. So every element of G is either green or orange, and the green ones are in H, and the orange ones are in the coset XH. So I would spend a minute just looking at this to try and make it clear.
Professor, can you explain one more time the Lagrange theorem, please?
The Lagrange theorem?
Yes.
Well, so this is the statement that if you take a finite group G and a subgroup H, the index, this is the number of left cosets, is the order of G, that means the number of elements in G, divided by the order of H, which is the number of elements in H. So in this case, the group G is the cyclic group of order 6. So the order of G is 6. And the subgroup H contains 3 elements. So the order of H is 3. So the number of cosets is 6 divided by 3, which is 2.
Thank you.
Let's look at another example with the same subgroup. So suppose G is, again, cyclic group of order 6. So x to the 6 is the identity. And now suppose I let H be the subgroup generated by x cubed. So this consists of the identity and x cubed. So if I look at the quotient group G mod H, the number of elements in this, again, is the order of G divided by the order of H by Lagrange's theorem. G has 6 elements. H has 2 elements. 6 over 2 is 3. So this group, the quotient group, will have 3 elements in it. So let's see, what are some of the elements? I have, first of all, H, or EH, which is E and x cubed. If I take the left coset XH, I multiply everything by x, everything in here. So I get x and x to the 4th. If I take the coset x squared H, I multiply everything in H by x squared. So I get x squared and x to the 5th. So these are 3 cosets of H in G. They're pairwise disjoint. No elements are common to the 3 of them. There are only 3 cosets. So these are the 3 cosets. And if I look at my group G, I have H, which consists of the identity and x cubed. I have XH, which is x and x to the 4th. I have x squared H, which is x squared and x to the 5th. So these are my 3 different cosets. I have the green ones, the orange ones, and the blue ones, right? So this is a very nice picture. Here's the group G, and it's divided into 3 subsets. Each subset is a coset. Every coset has 2 elements. 2 times 3 is 6. There are 3 cosets, and these are the elements in each coset. Now, okay, any questions? So I make the following little theorem. It says that H, I proved this last time, but it's worth repeating, that H be a subgroup of G if the index of G and H is 2, then always H is a normal subgroup. And I can show you the proof in a picture. If this is the group G, if this is H, there are only 2 left cosets. This is 1, so x times H. So for any x not in H, XH is different from H because x is in XH and x is not in H. So these can't be the same set. So for any x, this is a partition of G. But similarly, if I take the right coset, HX, HX is different from H, again, for the same reason. X is in here, but X is not in here. So XH is everything in G that's not in H, and HX is also everything in G that's not in H. So XH equals HX. There are only two cosets, and they're equal. So that is proof. So let's look at another example of a quotient group in the non-abelian case. Suppose I let G be the symmetric group S3, which in our standard notation consists of 6 elements: sigma, sigma squared, tau 1, tau 2, and tau 3, where sigma is the cycle 1, 2, 3. Sigma squared, which is the same as sigma inverse, is 1, 3, 2. Tau 1 is the transposition that fixes 1 and changes 2 and 3. Tau 2 fixes 2 and changes 1 and 3. And tau 3 fixes 3 and changes 1 and 2. So these are the 6 elements in this group. And suppose I let H be the cyclic subgroup generated by sigma. So this is the identity sigma and sigma squared. So the order of G is 6. The order of H is 3. The index of H and G is 6 over 3 is 2. So automatically we know, because I just proved that if a subgroup is index 2, H is a normal subgroup. So if I take the group S3, it's divided into H, and if I choose any element not in H, let's say tau 1H. And I've already calculated tau 1H, in previous lectures. Tau 1H is tau 1 times sigma, and tau 1 times sigma squared. And this, in fact, consists of the 3 transpositions. So my group H, S3, that's my G. I have E sigma and sigma squared, that's H. And then the coset tau 1H is tau 1, tau 2, and tau 3. So I have the green elements, which are in H, and the orange elements, which are in the coset tau 1H. Any questions about this? Just as another remark, I proved a moment ago that every subgroup is of an abelian group is normal. And the related statement is every quotient group of an abelian group is abelian. So the proof, so G, an abelian group, H a subgroup, which we know is abelian, if I take the coset XH times the coset YH, so this is for all X and Y in the group, XH times YX, that's the coset XYH. But the group's abelian. XY equals YX. So XYH is YXH, which is YH times XH. So the coset XH times the coset YH equals the coset YH times the coset XH. And that's the end of the proof. It says that coset multiplication is abelian.
Sorry, just to repeat, you said coset multiplication is abelian?
Right, for subgroups of an abelian group. It depends on the fact that the group is abelian. In general, quotient group is not abelian, but every quotient group of an abelian group is abelian. So if multiplication commutes in G, multiplication also commutes in G mod H for every subgroup H. Let's just recall we have a group G, let S be a subset of G, not necessarily a subgroup, but just any subset of G. And suppose we let, I don't know, script S be the set of all subgroups of G that contain the set S. So for example, G, the whole group is in S because a group is a subgroup of itself and the group contains S. So S is not the empty set. So what we call the subgroup of G generated by S is, and I put it in S inside brackets, it's the intersection of H for all H in S. This means this is the intersection of all subgroups of G that contain S. So we've already proved if you have any collection of subgroups of a group, the intersection is a subgroup. And S is contained in every one of these H's. So S is in the intersection. So this is a subgroup that contains S. And it's also the smallest subgroup that contains S. Because if you had any subgroup that contains S, this is contained in it. So this is the subgroup generated by S. And recall also the commutator of elements X and Y in the group is this element I write as XY in square brackets. This is X inverse Y inverse X times Y. So we already saw this, that I think it was even maybe on the, it was certainly on the review sheet and maybe on the midterm, that elements X and Y commute if and only if the commutator is the identity. So suppose we let S be the set of all commutators. So what is called the commutator subgroup of G is the subgroup generated by this set S. So the commutator subgroup, in practice, it might be very difficult to construct, but the commutator subgroup of a group is the smallest subgroup that contains all the commutators. And you might observe this is not considered an exercise. G is abelian if and only if this commutator subgroup, it's denoted as G comma G in square brackets, is just the identity. Because each one of these commutators is just the identity, and the identity element by itself is a subgroup. And we can make the following observation. Suppose we have H a normal subgroup of a group G. So G mod H, the quotient group, is abelian if and only if XH times YH equals YH times XH for all X and Y in the group, which is the same as saying that XYH, that's what this product is, equals YXH for all X and Y in the group. If I have XYH and YXH, if I multiply on the left by Y inverse, these are equal. If I multiply again on the left by X inverse, these are equal. But Y inverse Y is the identity, X inverse X is the identity, if and only if X inverse Y inverse XYH equals H for all X and Y in the group. This, of course, is just the commutator of X and Y. So if and only if this commutator times H equals H for all X and Y in the group, which is the same as saying that the commutator XY is in H for all X and Y in the group, which is the same as saying that the commutator subgroup, because if H contains every commutator, H is a subgroup that contains all the commutators, so it contains the smallest subgroup containing all the commutators, which is the commutator subgroup of H. So this is a nice chain of reasoning, and it proves the following theorem. The quotient group is abelian if and only if the subgroup H contains the commutator subgroup. Okay. All right, well, it's important to be introduced to the fundamental concepts of a subject. And we've been studying groups, but in algebra, you study objects that are interesting like groups, and also functions between them that are somehow relevant to the structure of the group. So that brings us to, in the notes, what is section 4 on what are called homomorphisms and isomorphisms. So a homomorphism is the following: let G and G prime be groups. A group homomorphism, or simply, when we're studying group theory and nothing else but groups, a homomorphism is a function f from G to G prime such that the following holds. If I take elements x and y in G for all x, y, and G, I can take x and y and I can multiply them, and then I can apply f to that. So it's like, here's G, here's G prime. I have elements x and y. I can multiply them, and I get the element xy. And then I have this function f from G to G prime. So xy goes to f of xy over in G prime. On the other hand, I could look at the image of x in G prime. X goes to f of x. Y, let's say, goes to some element f of y in G prime. And over in G prime, I can multiply them. See, let me make this picture a little bit bigger. It's like I have f of x, f of y, and if I multiply them, I get f of x times f of y. But I also have the element f of xy, and these have to be equal. So that's the definition of a homomorphism. For all x and y in G, f of xy is f of x times f of y. So a function f from a group G to a group G prime is called a homomorphism if it satisfies this sort of functional equation. F of xy is f of x times f of y. And then there's some special types of homomorphisms. If G equals G prime, so f from G to G, if it's a homomorphism, is called an endomorphism. Endo means inside, so inside itself, it sends G to G prime. If f from G to G prime is 1-to-1 and onto, then f is called an isomorphism. If f from G to G prime, f from G to itself is an isomorphism, that is 1-to-1 and onto, then we call F an automorphism. So in every subject, there's a vocabulary you have to learn. And in group theory, there's a homomorphism, and then there's special types. There are endomorphisms, that's a homomorphism from the group to itself. There's an isomorphism between groups, which is a homomorphism that's 1-to-1 and onto. If you have an isomorphism from the group to itself, that's called an automorphism. Yeah. And if F is 1-to-1, this is called a monomorphism. And if F is onto, it's also called an epimorphism, but that's just more vocabulary. It's all written down in the notes. So the simplest, the absolute simplest, if we take the function it's the identity function. Called ID for identity sub G. This is the function from G to itself defined by the X is always equal to X. Is a homomorphism. Because the identity applied to XY is XY. And X is the identity applied to X, and Y is the identity applied to Y. So the functional equation for homomorphism is satisfied. If G is abelian, then the squaring function from G to itself, defined by f of x equals x squared, is a homomorphism. Why is that? Because f of xy is xy squared. That means xy times xy, or xy. But yx, if the group is abelian, yx equals xy. So this is x times xy times y, or x squared y squared, which is f of x, f of y. So f of xy equals f of x times f of y. So squaring is a homomorphism, actually, then an homomorphism. What's another example? Suppose I take G to be the integers under addition and G prime to be MZ, that is the set of all multiples of M. Define the function f from G to G prime by f of x equals mx. I claim that G and G prime are isomorphic. Groups are isomorphic if there's an isomorphism between them. All right, so claim F is an isomorphism. See, why is that? First of all, f of x plus y is m times x plus y, which is mx plus my. Mx is f of x, and my is f of y. So that's the definition of homomorphism for an additive group. F of x equals f of y if and only if xm equals ym, if and only if x equals y. So this function is 1-to-1. And for all elements mx in G prime, f of x equals mx. So this function is onto. So these two additive abelian groups are isomorphic. Back when I was defining a homomorphism, I should have said that if G and G prime are additive groups, then this equation becomes f of x plus y equals f of x plus f of y. That's the analog of the multiplicative definition. So multiplicative groups, f is a homomorphism if it satisfies this. If the operation instead of multiplication is addition, these binary operation signs become plus signs. So these homomorphisms satisfy some very nice properties. So this is in the notes, written as a lemma. If we have three groups, G and G prime and G double prime, if f from G to G prime and h from G prime to G double prime are group homomorphisms, so we have this picture, if you like. Here's G, here's G prime, here's G double prime. I have this function f from G to G prime. I have a function h from G prime to G double prime. If I compose them, I get the function hf from G to G prime. So if f and h are homomorphisms, then the composite function hf is also a homomorphism. So let's just state the proof of this. If I take hf of xy, this means h of f of xy. That's the definition of composition. But f of xy is f of x times f of y. And because h is a homomorphism, this is h of f of x times h of f of y. This is hf of x times hf of y. So hf of xy is hf of x times hf of y. So hf is a homomorphism. If f and h are isomorphisms, then hf is also an isomorphism. And the proof is that suppose f and h are isomorphisms. Well, if f and h are 1-to-1 and onto, then HF is 1-to-1 and onto. So one of the facts about functions in general is the composite of two 1-to-1 functions is 1-to-1, and the composite of two onto functions is onto. And the third statement I want to prove, if f from G to G prime is an isomorphism, then there exists a function f inverse from G prime to G. In fact, a unique f inverse from G prime to G that is an isomorphism. And f composed with f inverse is the identity on G prime, and f inverse composed with f is the identity on G. Let's see. Why is that? Let me try and prove this again by drawing a picture. Here's G, here's G prime, here's a function f. So f is an isomorphism. So that means it's 1-to-1 and it's onto. And I want to construct an f inverse function that goes backwards from G prime back to G. So suppose I take a y in G prime. So because f is onto, this means there exists an x in G such that f of x equals y. There's some element x in G and y is equal to f of x. That x prime be any element in G such that f of x prime also equals y. So suppose we have another element x prime and f of x prime also equals y. But f is 1-to-1. So if f of x equals y and f of x prime equals y, then x equals x prime. So this element x is unique. There's no other element x prime. And so we can define f inverse of y to be equal to the unique element in x such that, so x is the unique element in G with f of x equal to y. And what is it if I take f inverse composed with f of x? That's f inverse of f of x. F of x is in G prime. F inverse is the unique element of G that gets sent to this, and that's equal to x. And if I take f composed with f inverse of y, f inverse of y is the unique x that gets sent to y. So f inverse of y, y goes to x, and the x is the one that goes to y. So f times f inverse is the identity on G prime, and f inverse f is the identity on G. So this F inverse is unique, and I have to show that F inverse is also a group homomorphism. So that Y1, Y2 be in Y, and F inverse of Y1 equal X1, and F inverse of Y2 equal X2. So this means that F of X1 equals Y1, and F of X2 equals Y2. So F of X1, X2, that's Y1, Y2. Oops, sorry, let me say this correctly. This is not incorrectly. So Y1, Y2 is F of X1 times F of X2, but because F is a homomorphism, this is F of X1, X2, which means that F inverse of Y1, Y2 is X1, X2. And X1 is F inverse of Y1, and X2 is F inverse of Y2. Now, again, this is all complete and correct, but it's all in the notes. But this is a lot to absorb in the beginning. Okay. Any questions about this yet? Let's see if I can construct another example of a homomorphism. Suppose I let G be the symmetric group S3. So E sigma sigma squared, tau 1, tau 2, tau 3, and let G prime be the multiplicative group 1 and minus 1. Right? This is just a group with two elements. 1 times 1 is 1, minus 1 times minus 1 is 1. Right? In this group is just ordinary multiplication. 1 times 1 is 1. 1 times minus 1 is minus 1. Minus 1 times 1 is minus 1. Minus 1 times minus 1 is plus 1. All right. That's the multiplication table for G prime. And define a function, I'll call it epsilon. Oh, no, I'll call it SGN for sine. From S3 to G prime as follows: the sign of the identity, the sign of sigma, and the sign of sigma squared is 1, and the sign of the three transpositions is minus 1. So here I have G. It contains the identity sigma, sigma squared, tau 1, tau 2, tau 3. Here I have G prime, which just contains the numbers 1 and minus 1. And this function, these three elements go to 1, and these three elements go to minus 1. This is my function. So every permutation is given is mapped to either plus 1 or minus 1. And these three go to 1, and these three go to -1. And you remember, if we took the subgroup H to be the cyclic subgroup generated by sigma, these three elements, that's just the subgroup H. And these three elements are the other coset, say tau 1H. So I'm sending everything in the coset H to +1 and everything in the coset tau 1H to -1. And this set is closed under multiplication. So if I take the sign of any product of these two things, it's 1. So for sigma I, sigma j in this subgroup H, the sign of sigma I times sigma j is the sign of sigma I plus j. That's just another element in here. That's equal to 1, which is the sign of sigma to the I, sign of sigma to the j. And if I take sigma to the I and some tau j, so sigma to the I in H and tau sub j in this coset, tau 1H, the sign of sigma to the I, tau sub j, that's just some element over here, that's -1, which is the sign of sigma to the I times the sign of tau j, because this is +1, and this is -1. 1 times -1 is -1. And if I take two elements in here, the product of two transpositions is one of these elements. So the sign of tau 1, tau I, tau j is +1, which is exactly -1 times -1. So in fact, this is a kind of laborious proof, but this is a proof that the sine function from S3 to ±1 is an example of a homomorphism. Let me give one last example of a homomorphism. Maybe two more examples, but let H be a normal subgroup of the group G, what is called the canonical homomorphism. Is a map pi from the group G, and if H is normal, there's a quotient group, G mod H. So this is defined by pi of the element X in the group is the left coset XH in G mod H. And why is this a homomorphism? If I take pi of XY, that's the coset XYH, which is the coset XH times the coset YH. And XH is pi of X, and YH is pi of Y. So pi of XH is pi of X times pi of Y. And that's the proof. That is the so-called canonical homomorphism. So for example, if G is the cyclic group of order 6, H is the subgroup generated by X cubed, which just contains the two elements X and X cubed. Then G mod H consists of three cosets, H, XH, and X squared H. And we have the map pi from G to G mod H defined by pi of any element is just the coset XH. So here I have G. It contains 6 elements: E, X, X squared, X cubed, X to the 4th, and X to the 5th. And G mod H consists of 3 cosets: H, which is E and X cubed, XH, which is X and X to the 4th, and X squared H, which is X squared and X to the 5th. This is G mod H. And my homomorphism pi sends E to H and X cubed to H. And it sends X to XH and X to the 4th to XH. And it sends X squared to X squared H and X to the 5th to X squared H. So this is sort of a picture of this homomorphism from G to G mod H. Okay. So if we reach what is in some sense the core of the subject of beginning group theory, which is groups, subgroups, normal subgroups, quotient groups, and homomorphisms. And again, you find all of this in the notes. I revised them slightly, and but it's up on Blackboard along with the homework for the next couple of weeks. All right. Any questions about this? I still have to post office hours for this week, but I'll do that sometime today. And have office hours probably every day after today. Okay. All right. If there are no more questions, if there are no questions, then we are done. Looks like a nice day, so hope everyone gets to enjoy it. All right. Bye all.